call is now being recorded.
Okay. So, in the last class, we have discussed the concept of Lagrange's multipliers, where we have seen the necessary and sufficient conditions for nonlinear programming problem with one and multiple constraints. In fact, equality constraints. Equality constraints. And for that purpose, we have defined the concept of Lagrange's multipliers and augmented Lagrangian function. Okay, so in the last class, there was a question that whether we can take it as a positive lambda. The answer is yes. In fact, Vijay has verified. So, and got the same result for this. So, for this purpose, for this problem, if you take here plus lambda and plus lambda 1 plus lambda 2, then the lambda values will be changed, but the optimal solution will not change. Okay. So, there we have seen that x1 was this value, x2 and x3, and after that we have found that optimal value z mean was this 0.847. That is the minimum value because this was as a positive, so that the particular delta for this Hessian matrix, so this would be because this was the equality constraint, so we do not know whether it is minimization or maximization. It was just written as optimize. So that is why we have found this Hessian bordered Hessian matrix and its minor of order 5, and then we have found that this is a minimization problem. And yeah, Vijay has sent me this solution that if we take positive lambda and then positive lambda 2, positive lambda 1, lambda 2, not positive, it is actually plus lambda 1 and plus lambda 2, then if we do the same calculation, you will get the same solution. So we can write it Lagrangian function as a, so yeah, so that's one remark for starter. Next, we have to understand if we have less than type criteria, the constraints are less than type, then what will be the necessary and sufficient conditions for non-linear programming problem with, that means non-linear programming problem with inequality constraints. So first we will discuss with one constraint and then with many. First one concept will be helpful to easy to understand. After that, we will generalize the concept. So just for historical note, so this was basically published in 1951, but then researchers have studied, they have discovered that the same idea was proposed in a master thesis in 1939 by Karush. So that is why these conditions are, most of the time it is called Kuhn-Tucker conditions, but it is also called Karush-Kuhn-Tucker conditions to give credit all the three persons. So probably next year you are going to study, you will have the whole year for a project, right? MTech second year project. So you will have to develop a master thesis also. Okay. So if you can, I don't think this is just a part of your MTech. So if you take it seriously, you can propose it. Okay. Although fundamental work takes several years of study and so much more dedicated work. So if you dedicate, maybe you can propose something, some new criteria, some new fundamental idea you can come up with. Okay. Okay, then. So let us consider the simple case. Okay. We have a function of n variables. We have only one constraint, which is less than type. Now, whenever it is less than, we by this time I think you have understood that maximization problem will have less than type criteria, because whenever we talk about maximization, okay, it is isometric to isometric means it is easy to compare that this is a profit function. Okay, so profit you will count based on some resource will be given, some resource constraint R1 or 2 or n resource will be fixed, and you have to use find this variables x1 x2 and xn, that particular vectors, so that within this resource you can maximize, you can use this much resource, so that you can maximize your profit within this limit. But whenever you talk about the minimization, automatically this resource will be, because we talk about the finite, the resource will be finite. Okay, whenever we talk about minimization, so this will lead us to the cost minimization. Cost minimization. Now, for example, cost minimization is related to the fact that you have to satisfy some minimal requirement. Okay, for minimum requirement, and then you have to find those arbitrary vector x. So that is why whenever we talk about minimization, the criteria will become greater than type. Whenever we talk about maximization, the criteria will be less than type. Okay. So this is by default the nature of the optimization problems. Now what we have to do again, now whenever we have a less than type criteria, what we need a slack variable. So we write it s square instead of s. Why? Because to ensure that it is always non-negative, and the constraint equation can be written as of this form. Okay. So gx minus b less equals to 0, which is actually of this form, and then we write the problem is now modified into this form. So we have modified this problem of this form, s square. This is a slack variable. Now again we define the Lagrangian function. What is the Lagrangian function? L of x, s, and lambda. Lambda is our unknown, s is our unknown variable, capital X is also unknown variable. And in order to find out the necessary conditions, what we have to do? We have to make the derivatives, partial derivatives equals to 0. So that means del L equals to 0, del L, and then del L. Yeah, so this time we differentiate with respect to all these variables and make them 0, partial derivatives. Because at a stationary point, these derivatives will be 0. Okay. So this is our first condition now. The second derivative will give us this form, and the third derivative will. Now from here, we have two cases. Okay. So this is minus 2s lambda equals to 0. So this will give us two situations. What is it? Either lambda equals to 0, or there may be some many cases actually, or s equals to 0. One of them is 0. If this is 0, then what it happens? We have here 0. So this implies minus hx plus s square equals to 0. So if you put 0 here, so this will imply hx equals to 0. Okay. Now if you combine these two situation, so this will lambda into hx equals to 0, which will again tell that either lambda 0 or hx 0. So we have to define this sentence in a way so that we want to eliminate s from the problem. Okay, so how do we do that? So now we have this situation. Okay, so for this purpose, what will happen now? Because we had hx plus s square equals to 0, and originally hx we had less equals to 0. So this is our modification we have done there. Okay, so this is very crucial step, because if you understand this step, then the next generalization will be easy to follow. So far we have here either this one is 0 or this one is 0. Either lambda 0 or hx 0. So if lambda is 0, okay, so this is what happens, because s square is non-negative, a square term is always non-negative. So if this is the case, then hx is non-zero. So if this is not, less than or equal to 0, then we have either it is strictly less than 0. If it is strictly less than 0, so then this equation lambda into hx equals to 0, what it will give us? This will indicate lambda equals to 0. So that means when lambda greater equals to 0, strictly greater than 0, then this hx is hx is greater than 0. So we reshuffle the conditions. What we had here, these three conditions now are modified into this. So first one is no problem. From second one, we had this one. Yeah. So from here, this is our second one. And then third one, what we have, this condition from here. Okay. And then fourth one, we will have lambda either equals to 0 or it would be greater equals to 0. So these are the necessary and sufficient conditions for Kuhn-Tucker necessary conditions. In fact, Karush Kuhn-Tucker necessary conditions of for a maximization problem. Now these problems, these conditions will be sufficient also if the functions are, for example, maximization fx subject to gx less equals to b. Okay, so this is a maximization, so that means it has concave. And this constraint is always, we try to take it as convex function, which will give a convex set also, that is convex region. If this is a minimization, then we will have a concave, sorry, convex function. It can also be case a where is non-convex. These three possibilities are there, but we will focus only this case, only this concave. So when this function is concave and the constraints are convex, then this necessary conditions also becomes sufficient conditions. Now, if we have a minimization problem, then the Kuhn-Tucker conditions for a minimization problem will be almost similar. So first and the second set of equation will be similar. The third is because this is a minimization, so we will have a greater than type constraint. So this is have satisfied. The only change will happen. I mean, not only change. There are two changes. This is less than and this is greater than. Sorry, hx is greater than equals to 0 and lambda is less than equals to 0. So this lambda multipliers, this Lagrange's multipliers will be negative for a minimization problem. And if you go back and recall the other case, there we had the option. We can take it for lambda 1 and lambda 2. We have not mentioned it anything. Okay, so if you go back and check, here we did not mention anything about the lambdas. So if you take positive plus lambda 1, then you will get some value. So lambda 1 was this is positive value. This is also positive. But if you take the other case, there you can see that lambdas are negative. Lambda 1 and lambda 2 are negative values. Okay, so this can happen. So that is why we have to go forward and conclude the necessary and sufficient condition for the constraint nonlinear optimization problem with inequalities. So these two changes we have to recall, we have to remember, and here the important factors are this. Okay, so these two functions should be remembered. So these are the conditions that I have mentioned already. That hx is always convex. Okay. Correct. For maximization, it will be less than, and for minimization, it will be greater than. Let us write hx, and the right hand side is 0. Or okay, then it becomes equal. Okay. So it is always convex. For maximization, fx will become concave if it is concave, and if it is convex, then we will have the separation. Okay. But if it is non-convex, then we have to find out the region for which the function is convex. It may not be convex over all the region or whole set, but it can be convex on a local domain. So yeah, so these are the two cases. which are very important for finding constant nonlinear optimization problems. Okay, so if you can consider this problem, z equals to this one, and subject to the constraint, only one constraint is given. Okay, so here it is. This is fx. Yeah, it is fx is written here. So this is our fx. Then this is hx. Now, one interesting thing that although we are using the Lagrangian function, although we are using this Lagrangian function, but we do not have to calculate this Lagrangian. We just have to calculate this f and h. See here, nothing is there. We do not have to calculate the L value. We just have to calculate these values. So our task is to put it into the actual format of the Kuhn-Tucker conditions. Okay. So this is hx, fx, and then we try to find out the solutions. So this, for example, this is fx del x1 minus lambda into hx del x1 equals to 0. Similarly, del f del x2 minus lambda into hx of del x2 equals to 0, and so on. So if you do this, what will happen? Del f del x1, it is 4 minus 3x1 square. So del f del x. Okay, so del f x2 we have to calculate. So this is what? Yeah, only 2. Similarly, we have to calculate this one. Del h del x1 is nothing but this is 1. Del h del x2, this is also 1. So now you have to substitute these values here and then try to find out this lambda values. Since only one constant is there, so we have only one lambda value we have to find out. So these functions will look like of this form. So equation 1, this is 2, this is 3 and 4, and lambda are greater or equals to 0. Because we have to satisfy this by the, yeah, so this is our condition. These are KKT. So we have to satisfy all these equations or inequalities. Here, 2 inequalities, 3 equations. So how do we get this solution? So we can see that this implies lambda equals to 2. So if you substitute here and if you substitute here, so this equation 1 and 3 will be transformed into some other equations. So there we will have, so then we will have like this. Equation 1 will give you so this is, or directly we can find out 4 minus 3x1 square minus 2 equals to 0. So 3x1, 4 minus 2, so this is 2 minus 3x1 square equals to 0. So x1 square equals to 2 by 3, and let us write 3. So directly we can find out x1. Similarly, we can find x2 from here once we find x1, and then we can find that the optimal point is this one. X star is our optimal point, and the optimal value will be this value, so 3.0887. So that's how we use Kuhn-Tucker conditions to find out the solution of a nonlinear constraint optimization problem with a single constraint. Now, if we have a nonlinear problem with more than one inequality constraint, then how to solve? First of all, we have to find out the Kuhn-Tucker conditions. Then we have to derive the conditions for a given problem. So, for example, if we have this problem 1, here x is our variable x1, x2, xn, and we have to find out the Lagrangian function I varies from 1 to m. So what we need is, we have to, in order to make it equal in these inequalities, we have to make hix here, hix less equals to 0. So we'll have hi 1 plus s1 square equals to 0. So we will have m different slack variables equals to 0. Yes, s square equals to 0. So this many slack variables we need. Not only this many slack variables, we need some multipliers also. So m different multipliers. So we define this lambda 1, lambda 2, and lambda m, and m different slack variables. Okay, so we define this Lagrangian function of this form and try to find out these unknowns. So for example, if we have x equals to x1, x2, s equals to s1, s2, then lambda equals to lambda 1, lambda 2, then we have 6 unknown to find out, 6 variables to find out. Okay, for example, so this is the simplest case that we can have, 6 unknowns for a multiple case. I mean, optimization problem with multiple constraint. Earlier we had only one constraint. There we had to find out. For the simple case, we have to find out how many variables? x1, x2, lambda 1, 3 variables. And also mu. So x1, x2, and s we don't have to calculate. Okay, the beauty of these Kuhn-Tucker conditions, we will take the help of s, but we will not find out. Without finding, so here we have to find out this lambda variables. Okay. So that's how it is actually the beauty of Kuhn-Tucker conditions. Although we can take s1 equals to s1 and s2, this is slack variables, we don't have to find out actually for finding the Kuhn-Tucker conditions. So we'll see that in a bit. So this necessary conditions we have to find out, right? We'll make them 0, and then sufficient conditions, again we make them 0, and finally then sorry, not sufficient, these are also necessary. All the partial derivatives with respect to xj, lambda I and si, we have to make it 0. That means in short form, this lambda L, x, lambda and s, you have to make them 0. Okay. So this will give us how many constants? Yeah. Similar to previous case. The same case that we'll use, that si and lambda I. If they 0, then either si 0 or lambda I 0. Si 0. And we'll use the same argument and try to find out the Kuhn-Tucker conditions. So if we do that, what will be the final sum conditions? So these are the final conditions. So lambda I into hi of x equals to 0. Since this is a maximization, so there will be a less than type constraint, and this multipliers will be greater or equals to 0. So the same idea can be extended to the minimization problem. So for minimization, okay, so these are actually greater or equals to 0. Constraints are greater or equals to 0. There is a mistake. This would be lambda I less equals to 0. This lambda i's will be less equals to 0. In fact, for a maximization problem, fx is concave and hix all are convex. So the hix is also, for this case also, it is convex. Okay. So for both cases, if we have these situations, then these necessary conditions are also sufficient conditions. They will guarantee the optimality. Now, if you try to look at one example here, how many variables? 2 variables. How many constraints? 2 constraints. 1, x1 and x2, and these are the variables. So, for example, we have to put it in the exam form. We don't need to find out the Lagrangian for Lagrangian function now, because this f and h1, these are sufficient. We have to find out this partial derivatives, all the partial derivatives, and try to find out this variables. Then if it is done, then we can proceed. Okay. So from here, del f del x1 is 14x1 plus 6. Del f del x2 is 10x2. So this is del h1 del x1 equals to 1. Del h1 del x2, this is 2. So for here, we can find del h2 del x1, this is 1. Del h2 del x1, sorry, 2. This becomes minus 3. Now you substitute these values. So this is 14x1 plus 6 plus, because this is x1, then for this x1 will be there. First we have to find out. Okay, for this one, what we are finding actually, del fx1 minus lambda 1 into del h1 del x1 minus lambda 2 into del h2 del x1. Okay. Equals to 0. So this is nothing but 14x1 plus 6 minus lambda 1 into 1 minus lambda 2 into 1 equals to 0. So this is simplified as equation 1. So this is the one. Similarly, we find out equation 2, 3 and 4. And we also write down these equations, the constant functions.
Sir?
Yes, tell me.
Sir, in the second equation, shouldn't the last term be plus 3 lambda 2?
Let me check whether there is a printing mistake.
Yes, sir, it should be plus 3 lambda 2.
This one,
Yes, yes.
last 3 lambda 2.
Yes, sir, because minus lambda 2 into derivative of h2 with respect to x2 itself is minus 3. So minus minus plus.
Just a minute. There may be some printing mistake. Okay. Yeah,
Okay.
let us verify. So this is 10 x2 minus this lambda 1 into what is it?
Lambda 1
1.
into 2.
Lambda 1 into
2. Dou h1
yes,
over dou
2
h2.
with respect to 2. So this is 2. Yeah, right. So this one, okay, this 2 minus lambda 2 into this one. So this is minus 3, right?
Yes, sir.
So now it will become 0. Yeah, so this is becoming plus. Yeah, right, plus. And then we have to write lambda 1 into this one. Lambda 1 into h1. Then lambda 2 into h2. And then h1x is this one. And h2x less equals to 0. Lambda 1, lambda 2 greater equals to 0. So all these equations are we have to calculate. Okay. So if you try to find out yeah. So what are the case since we have only two variable, two lambda, so there may be four cases, four different cases. Either both of them are 0 or lambda 1 is 0 but lambda 2 is non-zero, or it can be the reverse case. Lambda 1 is non-zero, lambda 2 is 0. If this is the case, then the last case is both of them are non-zero. Okay, so if you take first one, case 1, so this would be solution 1, lambda 1, lambda 2 are 0. Then the result, it will say, if you just put 0, 0, 0, 0 here, okay, so this is going to be x1 equals to 6 by 14 minus 6 by 14. But our problem is, our problem is greater equals to 0. X1 and x2 are greater equals to 0. Our resource constraints are, here it is. But we are supposed to get, this is positive, sorry, non-negative, greater equals to 0. So this is not feasible. Okay. Similarly, we proceed to the next candidate. Next set of possibilities. This is done. Now we have to consider this one. So if you take it, this is non-zero and this is, sorry, this is 0 and this is non-zero. Then we have to think. So that means delta 2 non-zero. If this is non-zero, then this part will be 0. Because product of two quantity is 0. One of them is non-zero, then the other is 0. So that is why we have to make it 0. Okay. So we write it from equation 4, we write it. And from 1 and 2, what we have to do is now, I think this cases may be incorrect. We have to verify. So from 1, 14x, 14x 1 plus 6. Lambda 1 we are taking 0 and lambda 2 we are taking minus lambda 2. Okay, right, that's fine. Okay. So we are putting here 0, 0 and 0 here. Okay. So because of this, what we are getting? This equation. Okay, so let us call it A. This is B. And for this one, we will have plus 3 lambda 2. 10x plus 10x2 plus 3 lambda 2. So yes, it is 3 lambda 2. So let us call it a 3. Now we can see here, this is a 3 by 3 system where three equations and 3 unknowns. So we can directly solve. Either we can use Gauss elimination or Gauss-Jordan method. But hand calculation will be difficult for exam purpose. If it will take much time. So if I give this type of questions in exam during the end exam, so what you have to do, you have to find out these equations and the solution of this 3 by 3 system or 4 by 4, whatever comes. So you can take help from Excel or computing tools to save the time. Or maybe MATLAB. But these equations are very important. You have to write these equations. Hand calculation is the system you have to write, but the solution you can, from this system, the solutions are getting. The solution step you can take help with the computing tools. Okay. In fact, the structure of this course is in such a way that we have to solve numerical problems. So, but if we think about a 3-hour exam or 2-hour exam, 2.5-hour exam, so that's not going to help to assess the cognitive level of the students. So whether they have understood or not. So whether you are understanding or not this, whether you are following the lectures or not, if you can write correctly these steps, then I will understand that yes, you have followed the lecture. Then you have at least you have understood. So that is the goal of this purpose. Goal of this course. Also, if somebody is claiming that this is our optimal solution, then everything will be go in vain. That means you have understood nothing because we are having this is a negative and this problem saying that these are positive. So feasible solution, infeasible solution. You have to recognize that you are not giving me or you are not giving to anybody that an infeasible solution as a optimal solution. Infeasible solutions cannot be optimal solution. Only feasible solutions can be optimal solution. So this is also not an optimal solution. third case that we have, if this lambda 1 is non-zero and lambda 2 is 0. Again, we are having a three equation, three variables. Solve it, try to find the solution. Yes. Now we can find this is a feasible solution. We can claim it a feasible solution. It satisfies all the non-negativity conditions. Okay. Okay, right. And we find out z value is this one. Finally, if we have both of them non-zero, so the system will become, this is non-zero, this is non-zero. So this will become 0 and this will become 0. So what we have? We have four variables, four equations. Again, we take help of computing tools. Okay. And then try to find out the solution. In this situation, we can find that the z value becomes 702.92. So between all the solutions, solution 1, it is infeasible, we reject it. Solution 2, it is also infeasible, so reject it. Solution 3 is feasible, let us keep it. And solution 4 is actually, well, let us keep it also. So between solution 3 and 4, which is maximum? Solution 4 is maximum. So this is our optimal solution. Okay. So this is how we use Kuhn-Tucker conditions to find out the optimal solution for a constraint nonlinear optimization problem with more than one constraint. Okay. Remember, this is plus. Okay. So this is plus. So try to solve it. Try to verify the results, and these are for your practice problem. I would say verify. Verify the results. Now there are actually, I could have started the quadratic programming also. So yeah, I will briefly introduce that what is quadratic programming. So that just to recall, what is our the simplex method. Simplex method can solve the problems as it can give you that optimal solution, unique and finite optimal. It can also give you alternative optimal. There are some unboundedness. Some problems will be unbounded. Some problems will be infeasible. Apart from that, simplex method can also be applied to solve a system of simultaneous linear equations. And it can also check whether a given system of linear equation, that system is dependent or not. That we have to, that can also be found by the use of simplex. Now, why I am going back to simplex method? Because whenever we will try to discuss the quadratic programming, what is the quadratic function? The highest power will be 2, right? Now, if you do that derivatives, if you differentiate this, then this becomes x 2x. So what is power is 1. So that means it becomes linear. Whenever we have linear, then we can use simplex method, or we can use simplex algorithm, or we can use, what is it called? Karmakar's method that we have seen earlier. So here also, now from here we have 4 variable and 4 equations. Now if I have to define this problem, okay, let me just put one more slide. Solution 4, we have this case. So let us delete this sentence and write minimize z equals to a1 plus a2 plus a3 plus a4, for which we are writing this. So this is a1 equals to 0 plus a2 equals to 0 plus a3 equals to 0 and plus a4 equals to 0. Because they are equality constraints is there, so we introduce artificial variables. Artificial variables are introduced. Now we have seen these artificial variables can be seen in simplex algorithm as well as in Kuhn-Tucker's method. Okay. So for a simple problem, for a small size problem, simplex method is more preferable compared to the Kuhn-Tucker's method. So if you have a 4 by 4 problem, so we can see this is a 4 by 4 system, and we are having that this one, that basis a1, a2, a3 and then 4 will form a basis, initial basis, and then we try to iterate. We write down the, so from there you can also find out the solution of this one. So that is another approach. Now when and how, actually this is the part of this is known as quadratic programming or Wolf's method. Wolf's method. Wolf's method uses Kuhn-Tucker conditions plus simplex method. By Kuhn-Tucker conditions, nonlinear programming, a nonlinear programming is transformed into a linear programming. Once we have linear programming, we can use simplex. So this Wolf's method, which is a part of quadratic programming, is very, very closely related to the Kuhn-Tucker conditions, because it uses both the benefits of Kuhn-Tucker conditions and the simplex method. Okay, so before we go to quadratic programming, let us see how this happens. So this is a system of linear equation. It is written as solve. How we can do? We can use the elimination process. We multiply some expression. For example, if we multiply with 1 and we multiply with 2, so then that is also possible way of solution, but we will use the simplex algorithm. So for simplex algorithm, instead of big M, what we'll take? We'll take minus 1. So this minus 1 are actually easy to handle. Big M tends to infinity. M tends to infinity is very difficult to handle, because computer will not understand what is infinity. Computer will understand whether 0, 1, or this type of words, this type of numbers. If you give infinity to computer, it will not understand. So that is why for computation purpose, we have to use minus 1 and minus 1 when it is a minimization. But if it is a maximization, we can call it a. But when this type of problem is there, our aim is to form that it should be 0, a1 and a2 should be 0. Only then it will be 0. Okay. The final basic solution will be 0. And then we can find this, apply this simplex algorithm, try, and then try to find out. This x2 becomes 3 and x1 becomes 4. In fact, if you try to find out here, so this is multiplied by 2, so this will become 4. This is 2, this is 22. Okay, then 4 gets cancelled. 3 minus 2, this is x2. Then this is 25 minus 22. So this is 3. So x2 is 3. Okay. This is an easy problem, but we have to understand this method, that simplex method can also be applied to find out the solution of a system of linear equations. Okay. If we have four variables, then it is not easy to understand. It is not easy to find. For that, we are doing the Gauss-Jordan. In fact, we have seen that this simplex method is nothing but Gauss-Jordan elimination. Gauss-Jordan elimination process. Okay. Now, if we have a situation like this, a system of linear equation. Now, if you look at these equations, okay, if you try to multiply by 2, this first equation, then what will happen? So this is 4, this is 6, and this is 12. So what is we going? What is happening? We can see that the first equation and the second equation are related by a multiplier. So if you try to understand this event in a simplex table, then you have to note that at the optimum level, when Cj minus Zj all are less than equals to 0, at the optimum table, one of the artificial variable will still be there. This will indicate that the solution is infeasible, which is, in other words, the system of linear equation are not actually, these equations are dependent. So that is why we are not getting any feasible solution. Okay, so with this idea, we'll move forward to the next topic, that is called quadratic programming. So that we will
Sir,
discuss in the next class. Just tell me.
sir, can you explain how by minimizing a1 plus a2 we find the system solution to system of equations? Like, I'm not able
Yeah,
to
this one.
understand how the process works.
This process.
Yes, so like by minimizing z equals a1 plus a2, how are we finding the solution to system of equations?
Okay, you know how to calculate this, right?
Ah, yes, sir.
Okay. So if you know this, then 50% task is over. Now we have to understand at the optimum level, what is the value of x1, what is the value of x2, and what is the value of a1, what is the value of a2. Now if you substitute these values 0 at the optimum level, so minimum z is 0. Okay. Our target is to eliminate. Okay, the function will be minimum. Our target is to make the minimum z equals to 0, and this our target is to find out x1 and x2. If at least one of them is here, for example a1 is there, then in the next case we have seen that this is a dependent system.
Okay.
We cannot solve this system. Okay. If the system is solvable, for example solvable, that means both the equations are independent. Okay, the system of linear equation, if their independent equations are there, then this will definitely happen. Okay.
Okay.
The next example, we can see that this is not not an independent system. So since this is a dependent system, so that is why we are not able to solve this system.
Okay. Okay. Got it, sir.
Okay.
Yeah.
So this
Got it.
is, I mean, this minimization function is like it is like a rocket launcher. Okay. After the launching the rocket, it will stay on the ground. The rocket will pass.
Okay.
It is just taking the support. It is just taking the support of this system, and it is giving the solution.
Okay, sir. Got it.
Okay. Right. So I'll stop here today, and in the next class we will discuss a quadratic programming problem, which is